Hi, in this video, we want to take a look at the negative binomial distribution. All right, so the negative binomial distribution is very similar to the geometric distribution, but there's a twist of things. Okay, so remember with the geometric distribution, it's like we flip a coin until we get our first heads, or we inspect items until our first defective items. Okay, so there, we're going until the first time we get a particular binary result. Okay, well, with a negative binomial, we're going to do the same thing. We're going to have trials until we get maybe our 5th result, maybe our 10th, our 20th, our 3rd, something like that. So imagine flipping a coin over and over and over until you get your 5th heads. Okay, so we want to know about the probability distribution. We want to know about the expected value and the variance. Okay, so well, one thing we need to have for this, we need to be able to say, we need to be able to assume that each trial, each flip of that coin, each flip is independent of all other flips, and they have equal probability of being heads or success on this one. Okay, so here what we're going to do, we're going to make this a little bit more general. We're not going to worry about 5th flip of heads. We're going to just say R, and R is going to be a parameter value. So here, this is the number of successes. P is going to be the probability of success on one particular flip. And so in this situation, the number of successes is known because there's R of them. The probability of success is known. The number of trials or failures, depending on how you look at it, is a random variable. So now, something I need to talk about is, remember that when we talk about the geometric distribution, one way is to count the number of flips total, including the last one. One way is to count the number of failures until we get that success. All right, well, they're equivalent to each other. They're just different presentations of the same thing. What we're going to do here, we're going to work with the number of trials total, so successes and failures. Now, they're equivalent to each other. There's a correspondence. There's just a shift in the formula for us. When you look at the literature can go both ways. And sometimes when I was looking online, I found articles that actually used both presentations in the same article. It was very confusing. Okay, so when you look at it, if you see that 0 is a possible value from a random variable, you immediately know that in that presentation it's counting the number of failures. If you see that the smallest possible value is equal to the number of successes, so the smallest possible value is equal to the number of successes, then you immediately know that it's counting the total number of trials in that presentation. And this is the one that we're going to use in this video. All right, so here, the probability of a particular value, okay, there's a lot to unpack here. It's going to be the probability of success on one flip to the power of R times the probability of failure on a flip, X minus R, and then we're going to have this binomial coefficient of X minus 1 choose R minus 1. And then our random variable can be R or R plus 1, R plus 2, and so on. Okay, so that gives us the probability distribution. Our expected value is going to be R over P, and our variance is going to be R times the probability of failure on a flip divided by P squared. Okay. So something we need to ask ourselves, does this define a probability? Yes or no? Okay, so now what I'm going to do, I'm not going to actually do a formal proof of this. I'm just going to give you an argument that hopefully convinces you that yes, this will define a proper probability. Let's consider this particular sequence of flips. So here, we're flipping a coin until we have 5 heads. And every time I have heads, I put S for success. Every time I have tails, I put F for failure. All right, so we notice that I have FS, I have FFS, then S by itself, then FS, and then S by itself. So I can look at this, I can see this as the manifestation of 5 geometric random variables. So here, there were 2 trials in the first geometric random variable. There were 3 trials in the second, 1 trial in the third, 2 trials in the fourth, and the last one had just 1 trial. Okay, so let's think about the probability of exactly this sequence, exactly this particular one, if I'm flipping a coin. Every time I see an F, well, that was a probability of 1 minus P. Every time I see an S, that is a probability of P for success. All right, and so if I take this, every time I see an F, I put a 1 minus P. Every time I see an S, I put a P. I get exactly this sequence of probabilities multiplied out. All right, well, that corresponds to 1 minus P to the power of 4 times P to the 5. So there were 5 successes, so it's P to the 5. There were 4 failures, so that's 1 minus P to the power of 4. Now, this is one possible way to get 5 successes from 9 possible trials. Well, how many ways could I rearrange this sequence and still get 5 successes in 9 trials? Well, the first thing we need to think about, we need to realize is that I'm flipping a coin until I hit my 5th heads. All right, well, if I'm going until my 5th heads and then I stop, I know that my very last flip was a success. So I know that the very last position is an S. Or if the very last position is an S, the rest here have to be 8 trials and 4 successes. All right, well, how many ways can I rearrange 8 trials with 4 successes? Well, that's going to be a binomial coefficient. That's going to be 8 choose 4 right there. I'm having trouble highlighting. Oh, I guess. There we go, 8 choose 4 right there. Okay, well, let's think about this in general. Let's say instead I had R successes and X total trials. All right, well, in that situation, I have, R successes, X minus R failures. And you'll notice that using the same line of reasoning, we have P to the power of R. We have 1 minus P to the power of X minus R. So this part is addressing the probability of the individual successes, that there are of them. This part addresses the probability of failures of X minus R of them. Now, how many ways could I rearrange the terms and get the same negative binomial random variable? So remember, I take my very last position, and that has to be a success. Well, if the very last one is a success, then I have X minus 1 trials that can be rearranged, and I have R minus 1 of those are going to be successes. So then I can see right there that X minus 1 choose R minus 1 gives me all the possible ways that I can switch around the first, all but the last flips of the sequence. Okay. And so that is how we get the formula. And so here, this is how we get it. So this is the number of ways that I could rearrange a particular sequence and get the same negative binomial value. And so remember, when I'm talking about negative binomial, I don't care about the actual sequence of success and failures. I care about the total number of flips. And so since I don't care about the exact sequence, I need to take all of them that give me the same number that I want, and I put them together. This part addresses the probability of the successes. This part addresses the probability of the failures. All right. Now let's think about the expected value. Okay, for the expected value, I'm not going to go at it directly. What I'm going to do, I'm going to think about, negative binomial is the sum of geometric random variables. So if I have R successes for my negative binomial random variable, then what I get as a random variable has to be the sum of r different geometric random variables. Okay, so what I'm going to do, I'm going to say that w sub I is a geometric random variable, and I'm going to say that my negative binomial random variable is the sum of those w's. All right, so once I do this, one thing that's very nice, since it's addition, expected values come out very nicely, because remember, expected values come from integration, and if I have the sum of terms being integrated, I can break that into a sum of integrations. So when I take the expected value of both sides of the equation, this part breaks up into, so the expected value of the sum is the sum of the expected values. Now, I remember that each of these is a geometric random variable, so I replace the expected value with the expected value. So I get 1 over p for every single one of these. And now I have a sum of the same term over and over and over. Well, that's just multiplication, right? So I'm going to multiply 1 over p by the number of terms in the addition, which is r. Boom, we see the expected value of a negative binomial random variable is r over p. Nice. All right, so now what about the variance? The variance, I'm going to do the exact same trick. It's just that here I need to emphasize that when I break up the variance, I need to have that the geometric random variables are independent of each other. All right, so once again, I set x equal to the sum of geometric random variables. I take the variance of both sides of the equation. So the variance of the sum of independent random variables, very important that these are independent random variables. The variance of the sum of independent variables is the variance of the sum, or sorry, the sum of the variances. I'm misspeaking that. Follow the equations. All right, so now I replace each of the variance terms with the variance here. See, this replaces the variance of W1. And then I realize I have r of them. Boom, we've got it. Now, what about if I want to count the number of failures instead of the number of trials? Well, it's very easy. All I have to do is do a location shift on the function. So if I'm going to shift to the left, remember from college algebra, we do like addition if I want to shift it to the left, and I have to simultaneously subtract off on the domain. And so I execute that here. It'll give me what I want. I notice that the domain has shifted appropriately. Also, I have to shift the expected value because the entire distribution is moving over, but the variance stays the same. Variance does not change under location transforms. All right, well, that's all I've got for you. Take care and goodbye.